ultrasound system is taking away those low-level echoes, right? So it's also taking away useful information as far as like not being able to process those low-level reflections. Okay, so therefore we're not gonna get all the meaningful information we need. Okay, so give me another another consequence of using the vacuum material.
Wide bandwidth.
Wide bandwidth. What? Tell me about that. What's up with wide bandwidth? What's up with that? Tell me about it.
Wide bandwidth because it creates shorter pulses.
Okay. Okay.
So that's why it has wider bandwidth. More.
When we talking about bandwidth, that has more to do with, the resonance, right? When we talking about resonance, we're talking about it being able to vibrate at its main frequency, guys. Resonance is another term for main frequency, okay? So when we're talking about having a wide or narrow bandwidth, we're talking about the ability for it to be able to operate at its main or resonant frequency. When it has a wide bandwidth, meaning that it's operating at a wider range of frequencies. Remember, that's what our term is when we're talking about bandwidth. That's what bandwidth means, is wide range of frequencies. So when it has a wide bandwidth, meaning it has a wide range of frequencies. So even though it's a 5 transducer, it may operate between 1 and 8. That's the operating range of that transducer. So when we're talking about having a wide bandwidth versus a narrow bandwidth, if they both are 5 transducers, then that wide bandwidth is going to operate at a wider range, but that narrow bandwidth is going to mostly operate at the 5 frequency or narrower range of frequencies. Okay. So also that has to do with, say, we're talking about continuum versus pulse wave. Us using pulse wave transducers, you're on the right track because we do like short pulses, right? We do like short pulses, and the damping material, the way it's stopping the vibrations or stopping that sound, it's not going to stop immediately.
Yeah.
So it's going to operate at a wider range of frequencies, okay? With our imaging transducers, okay? With our imaging transducers, it's going to operate at a wider range of frequencies. Or we're going to have wide bandwidth or broadband, right? Broadband is another term for wide bandwidth, okay? So when we're talking about our narrow bandwidth, meaning that it's the resonant frequency, it's the transducers operating at the more closer to the resonant frequency. Narrow bandwidth is say there's always going to be a range of frequencies, right? Because it's oscillates. It's always going to be going up and below because the sound waves oscillate. They go up, they go up and down. So we're talking about a continuous wave transducers. They're going to operate with narrow bandwidth. Okay, continuous wave transducers and therapeutic transducers operate with with narrow bandwidth. Okay. Say that again, guys. Continuous wave transducers and therapeutic transducers operate with narrow bandwidth. Okay. Our imaging transducers, they're going to operate with a wide bandwidth. Okay.
The pulse is with what?
The pulse?
Pulse transducer with wide range.
The imaging probes are what we use in diagnostic ultrasound. They're going to have a wide bandwidth.
Yeah.
Wide bandwidth. That's because the sound is going to dampen out, right? The sound is going to, with our continuous wave, it's going to constantly be continuous. With our pulse wave, it's going to be, right? Because it's going to have to be damped. It's going to have to be stopped, and then we need to listen. And then we're going to. So this will be a range of the frequency, right? Actually, I didn't draw that. I didn't draw that as good as I wanted to. That's not a great marker anyway. Because it's being damped, and also that's going to change the frequency. Remember, frequency is the beginning of one cycle to the beginning of the next cycle. So when it has a wide range, meaning that this is from right here to right here, that's the cycle, right? That distance is that time is going to be the same, or distance is going to be the same with each cycle. From here to here, that's different. From there to there, that's different. See how the range of that frequency is different? That's what we're talking about. We're talking about wide bandwidth versus narrow bandwidth. Narrow bandwidth meaning it's going to operate at the resonant frequency most of the time.
Which one's the wide band? The bottom?
The bottom, the pulse wave, that's what we use with diagnostic ultrasound. It has a wide bandwidth because the range of frequencies are different.
Range, what you mean by range?
That's what bandwidth means, range of frequencies. Meaning that our frequencies are not the same, consistent throughout. Like the top example, the wavelengths between those two, they're exactly the same no matter what, right? The frequency of this sound, it's exactly the same. Continuous wave, it's continuous. It is not dampened. It's not gonna have to be stopped so we can listen. So when it stops, it's not gonna just stop all at once, right? It's not gonna boom, immediately stop. Right? It takes some time to stop that sound, right? So when you have the damping material, the frequency between those wavelengths is gonna get shorter and shorter and shorter. Okay, all right? Yes, ma'am.
What was the difference between the axial resolution and the longitudinal resolution? I saw them in the book.
Longitude, we haven't talked about longitudinal
They
resolution.
use interchangeably.
Where is that at?
I saw it. I don't know if it's in a book somewhere.
We haven't even gotten there yet, Pat.
Okay.
No, it is axial resolution right now.
All right, very good.
I'm not gonna fool you yet. We don't get to longitudinal, lard and ladder until to chapter 10, I believe. We're talking about axial and lateral resolution. No, it just is axial resolution right now. Speaking of axial resolution, what determines axial resolution, Pat?
Determined the axial resolution was the. Was it the key factor?
The who? I haven't even talked about that today yet.
No,
Not the
wait,
key
I don't
factor.
know.
Somebody help her out. What determines the axial resolution? We've been talking about it since chapter 3. What determines the axial resolution? Chapter 4, I mean. There we go. What was that one as? Spatial pulse length. The spatial pulse length determines the axial resolution. This should be in y'all notes because I've said this like 3 times. I told you to write it down. The spatial pulse length determines the axial resolution.
Right, because you want a shorter pulse.
Absolutely, absolutely. I want shorter pulses. So that's like saying
But the long pulses deteriorate the image, is that true?
yeah, absolutely. So when we're talking about axial resolution, again, axial resolution is also equal to half of the spatial pulse length, or the spatial pulse length divided by 2 will give you the axial resolution. So looking at these two pulses, these two waves right here, which one of those will provide us with better axial resolution?
The bottom.
The bottom one, right? Because the spatial pulse length is short. Okay? The length of this pulse from here to here is short. Okay? That's gonna have better axial resolution. Okay? So axial resolution is determined by the spatial pulse length. Okay? We're kind of getting into that a little early, but axial resolution is determined by the spatial pulse length. All right? So back to our consequences, guys. We talked about 2 already. We talked about, decreased sensitivity. Why? Because the backing material during reception, the transducer dampens the sound and is less able to convert those low-level sound reflections into electrical signals. Remember, when the sound comes back, during reception, that's the piezoelectric effect, right? Taking those pressure waves and making our PZT vibrate to create an electrical signal, right? So it decreases sensitivity because it's not able to process those low-level sound reflections that we get. All right, that's our decreased sensitivity. I want you guys to know those 3 100%. Okay, and backing material also another consequence is the wide bandwidth, the wide range of frequencies because of the damping material. It's not gonna be at a consistent resonant frequency. It's not gonna vibrate freely for a long time, right? So we like short pulses in imaging, in diagnostic imaging, right? So resonant frequency, guys, again, also means the main frequency. Okay, so we have a 12 megahertz transducer. 12 megahertz is our resonant frequency. That's our main frequency. But a 12 megahertz transducer may also operate at 13 megahertz. It may also operate at 10 megahertz. okay, at some point. All right, but the main or resonant frequency is 12 megahertz. Okay. So us having a wide bandwidth, instead of getting just long continuous, sound waves, we're gonna get that short duration or that sound click instead of a long steady tone, long steady vibrations. All right. That's on figure 8.2. I remember I drew that on the board for you. Just think of, like I said, think of, me and Bree, tall, slim, narrow bandwidth, me, short, fat, wide bandwidth, right? Okay. Wide range of frequencies, broad band, Bree, narrow bandwidth, all right? So, again, long duration events equals narrow bandwidth. Okay? Long duration events equals narrow bandwidth. And short duration events, meaning our short pulses, are going to equal wide bandwidth or broadband. All right? That's our example right there. See how our blue is the wide bandwidth. The X would be the range of frequencies. Okay, the X would be the range of frequencies. Okay, so they may be the main. You see they share. It look like they share a common main frequency, right? They share a common resonant frequency right here, but this one has a wider range of frequencies compared to the narrow bandwidth. So again, wide bandwidth, that would be our imaging transducers. Narrow bandwidth, that would be our therapeutic or our continuous wave transducers that have narrow bandwidth. That bandwidth also means what, Farnaz? What does bandwidth mean? Bandwidth? Somebody help her out? A range of frequencies. A range of frequencies. Dewey, what's another term for the main frequency?
The main frequency?
Somebody help them out. Somebody help them. The resonant frequency.
Oh, resident.
Resonant frequency. What's another term for the main frequency? The resonant frequency.
It's easy, bro.
Okay. All right. Here it is right here. We already kind of talked about this with, light damping versus heavy damping. Okay. And again, this illustration a lot better than the way I drew it, right? This is, you see our wavelengths, they stay the same no matter what throughout this this sound right here. This could also be a pulse too, right? This pulse and this pulse. That's not to say that, but the difference is, see the frequency amongst this pulse is different. It's not the same frequency throughout this entire pulse. Okay? That's what's going to determine narrow versus wide bandwidth. Wide bandwidth is going to have a wider range of frequencies. Okay? The frequency of this sound pulse is the same throughout. All right? We good there, guys? I know I'm covering it heavy, but I want to make sure we understand the difference between wide bandwidth, narrow bandwidth, what is used, what transducers use narrow bandwidth, what transducers provide wide bandwidth or broadband. Okay. We good on that?
So basically, resonant frequency can also be known as the narrow bandwidth, even though it's vibrating like freely and constant.
But you can also have, if let's say for instance, if I have a bigger damping block or or light damping, I'm still going to provide pulses. So that's why resonant frequency is known as the main frequency, because no matter what, sound waves oscillate. So it's never going to be constantly like boom 12 megahertz exactly the whole time. It's always going to have a small offset because it's oscillating, going up and down, right? It's going up and down. These events are occurring. How sound waves go? They're going compressions, rarefaction. I'm sorry, compressions, rarefactions, compressions, rarefactions. So even though they have a main frequency, even though it's narrow bandwidth, it's still going to have a little range, right? It's still going to be a range to that main frequency. Okay, just the wide bandwidth is going to operate at an even wider range of those frequencies. So that's why. So this right here, whatever this number is right here in the middle of this frequency, that would be the resonant frequency because that's the main frequency. That's the main frequency. Okay, so let's talk about Q factor, guys. So Q factor and bandwidth, they're related. How are they related? They're inversely related, okay? Okay. So if I have wide bandwidth, that means I'm gonna have a low Q factor. Remember we talked about this. Why? I'm gonna have a low Q factor because my wide bandwidth transducers are gonna be less likely to operate at the main frequency. Then that Q meaning quality factor, that means the quality of that sound is going down, right? Because it's not operating at the main frequency that we want it to. Okay, so quality factor, guys, a unitless number, like percent, right? Unitless number that is inversely related to the bandwidth, okay? Just like, what else is inversely related? PRP and PRF, inversely related, right? So mathematically, the main frequency divided by the bandwidth will give you the Q factor. So if we have a main frequency of, let's say we have a transducer that has a main frequency of, let's say, 5 megahertz, but it has a low frequency of 2 and a high frequency of 7. It's gonna be too easy. Okay, too easy because it's gonna make it even. You'll see what I'm doing in a second. So, what is our bandwidth? The difference. Remember, determine the bandwidth is the difference between the highest and the lowest frequencies, right? So the difference between 8 and 2 is 6, right? 6 would be our bandwidth. So determine our Q factor is going to be the main frequency over
bandwidth.
the bandwidth. Somebody pull their calculators out for us. So our main frequency is 5 over 6. That is about
0.333.
That's 70.
1.6.
It's 6. That's 70.
0.83.
79.9 or something?
0.83.
0.83?
Yeah.
0.83. 0 equals 0.83. And that would be our quality factor. So that would be a pretty good quality factor right there. It's pretty high, you know.